In this video, we're going to be talking about Hess's Law. Hess's Law is a tool that's used in determining different types of enthalpies for reactions. All right, so essentially what Hess's Law states is that it doesn't matter whether you're going straight from products or reactants or going through some intermediate. The only thing that matters is the total enthalpy of the final state and the total enthalpy of the starting state. And essentially what this is going to let you do is figure out enthalpies of reactions that we can't measure directly by essentially summing up some component reactions. All right. So sometimes Hess's law is demonstrated graphically like this. All right. We could either go straight from A to C, but we could also show A going to B and then B going to C. But what Hess's law says is that A to C is essentially the same thing as the sum of A going to B plus B going to C. All right. So sometimes it's shown graphically like this, but when you're applying it, it's much easier to show it as essentially a series of reactions where you're going to be adding these things together. All right, so the overall reaction here is A going to C. So that's what I've shown right here. All right, and what we're showing is the two component reactions, A going to B right here, and B going to C right here. All right, and if we take these two component reactions, hopefully you remember things from the past where we can, if you see something on a reactant side, it would cancel with something on a product side. So we could cancel out B so that the overall reaction when these are summed up together is just A going to C. All right, and that's what we're trying to determine here. And so the total enthalpy of A going to C is going to be the sum of the enthalpies. All right, and that's the key part about Hess's law, is that the total enthalpy of a reaction is just the sum of the enthalpies of the component parts to it. All right, so most of the work that actually goes into applying Hess's law goes into setting up your component reactions so that essentially things are going to cancel out so that you're going to end up just with your overall reaction. All right. So before we get into that, a couple of rules for manipulating these component reactions. So this is where we're actually going to be applying the enthalpies of combustion and the enthalpies of formation that we learned about in the previous video. First of all, if the reverse direction of a reaction is shown, you can do that, and all you have to do is change the sign of delta H. All right. So for example, if this might be a type of component reaction that we use in Hess's law, and all this is the reverse of a combustion reaction. Notice that on the right side, right here, we've got methane and oxygen, so that's methane combining with oxygen. And on the left side, we show the normal products of combustion, carbon dioxide and water. And all this reaction here is the reverse of this. All right, so take these, put them on the left, take these, put them on the right. And if this is the standard enthalpy change of combustion for this reaction, then if we show it as the reverse, all we have to do is change the sign. All right, so we're going to go from a negative 891 to a positive 891. All right, so the other thing is sometimes you might occasionally need to multiply things by a certain factor. All right, and if you do that, you're just going to multiply the delta H as well. All right, so for example, if you take a look at the standard enthalpy of combustion for methanol right here, all right, we have this. All right, so but if sometimes when we're trying to set things up so that things cancel out, if we had 2B here, we couldn't use just this right here. We might need to multiply everything by 2 here so we get that 2 coefficient so that things would cancel out. So if we took this reaction right here and we multiplied everything by 2, all right, notice, we'll just remember that number for a second. All right, notice that everything here got multiplied by 2. All right, so these were our new coefficients. and all we end up having to do is multiply that delta H by 2. All right, so that's why we get this larger number. FYI, according to sig fig rules, I should probably round this to minus 1.4, so 1,450 instead of 1,452. All right, so so here's an example of the value of Hess's law. Sometimes it allows you to determine enthalpies that can't be determined directly. So for example, if we wanted to figure out what the standard enthalpy of combustion of carbon going to carbon monoxide is, we can't do that directly. All right, so if we took some carbon and we tried to just burn it with a little bit of oxygen to get carbon monoxide, we can't do this directly. All right, and the reason that we can't do this directly is inevitably, if you've got oxygen around, some of the carbon is going to make carbon dioxide. So it's almost impossible to do this with, and only get that one reaction to occur. All right, but there's a couple things that we can do. We can take carbon and we can burn it in an excess of oxygen and we can make carbon dioxide, and we know the standard enthalpy of combustion of that. And also, if we have a sample of carbon monoxide, we can burn that with oxygen and we can get carbon dioxide from that, and that is a known enthalpy of combustion as well. All right, so these are two reactions that we can do, and we're going to apply Hess's law to try to figure out an enthalpy of combustion for this reaction right here. All right, so again, going back to our strategy here, we have an overall reaction, and what we want to do is we want to set up our component reactions so that things will cancel out, so that when we add these component reactions together, we'll end up getting our overall reaction. All right, and it'll take a little bit of practice to get used to this, but let's see what we can do. All right, so first of all, take a look at where things are in the desired reaction. All right, we've got a carbon all by itself on the left here. All right, so when we look at these, I can find this one right here, which has got the carbon all by itself on the left. All right, so that's probably going to be left as is. All right, and our something else we have here is we've got carbon monoxide on the right. Well, in our component reactions, we've got carbon monoxide on our left. All right, and that's not where we would want it if we're trying to get to something that's got carbon monoxide on the right. But what we can do is apply that rule which says, okay, we can take this thing and we can flip it around. All right, and all we have to do is change the sign of this enthalpy. All right, so that's what we're going to do here. We're going to write the reverse of that, and we're just going to change the sign. All right, so these are now the two component reactions that we're going to end up using. All right, so taking a look at these, all right, are there things on the left and the right that we can cancel out? All right, well, notice we've got a carbon dioxide on the left here, and we've got a carbon dioxide on the right here. So these two guys right here, we can cross out. All right, so those are now crossed out. All right, so we've also got oxygen here, and we've got 1/2 of oxygen here. All right, so even though we can't completely cross them out, if we cross out what we can, this guy would get crossed out, and that would leave 1/2 of an oxygen left over here. All right, so once we do that, so once we end up canceling out that 1/2 of an oxygen and add things together, notice that this carbon comes down, we have our 1/2 of an oxygen left over, and we have carbon monoxide here, and this 1/2 of the oxygen got canceled out. All right, so notice that what we have is now the overall reaction. All right, so in order to calculate the enthalpy change for this reaction right here, we apply Hess's law, which states that all we have to do is add up the component enthalpies, and that will give you the calculated enthalpy that we want. All right, so again, when you're applying Hess's law, there's actually more effort being devoted into setting up your component reactions so that things will cancel out. And if you set those up correctly and you do the correct things to their enthalpies, the end will just be a simple addition of the enthalpies, and this will become easier when you see a couple of examples of this done.